Welcome to the lecture series of boundary value problems. Today we are going to see type 2 problems under boundary value problems. What is type 2? Type 2 is problems on vibrating string with non-zero initial velocity. What is our type 1? Type 1 is displacement function will be given in the question and initial velocity is 0. That is our type 1. So now type 2 problems are problems on vibrating string with non-zero initial velocity. That means initial velocity will be given in the question and displacement function is 0. That is our type 2 problems. So what are the boundary conditions for type 2? The first boundary condition is y of 0 comma t equal to 0 for all t greater than 0. And the second condition is y of L comma t equal to 0 for all t greater than 0. These two conditions are same for both the type. The third condition is y of x comma 0 equal to 0 for all x in 0 comma L. And the fourth boundary condition dou by dou t, that means velocity. Dou by dou t of the displacement function, that is equal to g of x for all x in 0 comma L. Here I have written g of x, you can write f of x also. To give the difference between type 1 and type 2, we have taken here g of x. If you want, we can take f of x also, it doesn't mean. So this is the type 2 boundary conditions. So under the type 2 problems, first condition and second condition applying the general solution, we can get the same type of answers. Only differ in the third and fourth boundary condition. So that is what the difference between type 1 and type 2. Hope now you can understand what is type 1 and type 2 problems. Now we will go for the first problem under type 2. Look at the question. If a string of length L is initially at rest in its equilibrium position and each of its points is given the velocity dou y by dou t at t equal to 0 equal to v naught sin q pi x by L such that 0 less than x less than L. Determine the displacement function y of x comma t. So this is what the question under type 2. You can see that the question itself, the displacement, that is the initial velocity is given. Here there is no discussion about the displacement. So from this only you can identify whether the question belongs to the type 1 or type 2, because here velocity is given, initial velocity is given. So this problem comes under type 2 problems. So what is the first step? As similar to the type 1. What is our first step? First we have to write the one-dimensional wave equation and then we have to write the correct solution, then boundary conditions, the same kind of procedure. So look at the solution. The one-dimensional wave equation is dou square y by dou t square equal to a square dou square y by dou x square. We can call this as equation 1. The boundary conditions are, first boundary condition y of 0 comma t equal to 0 for all t greater than 0. The second one is y of L comma t equal to 0 for all t greater than 0. And the third boundary condition is y of x comma 0 equal to 0 such that 0 less than x less than L. And the fourth boundary condition is velocity, initial velocity equal to v naught sin q pi x by L, 0 less than x less than L. So next step we have to write the boundary condition. Now the general procedure, the correct solution of equation 1 is y of x comma t equal to c1 cos px plus c2 sin px into c3 cos pat plus c4 sin pat. We can call this as equation 2. So what is the procedure? First we have to apply the boundary condition 1 in equation 2. So apply boundary condition 1 in equation 2. So what is our boundary condition 1? Y of 0 comma t equal to 0. That means what? We have to put x is equal to 0. That is our boundary condition 1. That is, we have to put x is equal to 0 in equation 2. So what will happen? The left hand side will become as y of 0 comma t, because x is equal to 0 equal to wherever x comes. Here look at this, c1 cos px, that means c1 cos 0. Cos 0 value is 1, so we can get c1. Cos 0 value is 1, so we can get c1. Sin 0 is 0, so we can get c2 is 0. So c1 into 1 plus c2 into 0. Here there is no x, so we can get the terms as it is. That is C3 cos PAT plus C4 sin PAT equal to what? Equal to 0. That is our boundary condition. So in this one we can get which is equal to C1 into C3 cos PAT plus C4 sin PAT equal to 0. So from this we have to give the conclusion which one is 0. We know that already we have discussed in our type 1. We know very well that C3 cos PAT plus C4 sin PAT which is not equal to 0, right? So from this what is our conclusion? This is not equal to 0 means obviously, which implies C1 equal to 0. So now after applying the boundary condition 1, we got C1 equal to 0. So what we have to do? We have to substitute the C1 equal to 0 in equation 2. So our displacement function y of x comma t equal to C1 equal to 0. So substituting here C1 equal to 0, we can get the whole term will become 0. Only we can get C2 sin px into remaining 1. So what is the answer? C2 sin px into C3 cos PAT plus C4 sin PAT. We can call this as our equation 3. So now what we are going to do is, we are going to apply boundary condition 2 in our equation 3. So the next boundary condition, apply boundary condition 2 in equation 3. So what is our boundary condition 2? Boundary condition 2 is y of L comma t equal to 0. That means x is equal to L. So that is what we have to substitute in this equation. So if you want, you can write it in the bracket, put x is equal to L. So the left hand side will become y of L comma t equal to C2 sin PL, because here only x is there, remaining all the place there is no x, into C3 cos PAT plus C4 sin PAT equal to 0. Okay, so here also already we have discussed that C3 cos PAT plus C4 sin PAT which is not equal to 0. So what will happen? Here we can get C2 is a constant, and already we have written C1 equal to 0, therefore C2 is also not equal to 0. So since C3 cos PAT plus C4 sin PAT is not equal to 0, already one constant is 0, therefore C2 is also not equal to 0. So what is the only possible to be 0? Sin PL equal to 0. So this is the only possible. So for what value sin will become 0? Only for the values of multiples of pi, sin will become 0. So we can compare the sin PL equal to 0, which is equal to sin n pi. So from this we can conclude that PL equal to n pi. So P is equal to n pi by L. So this is what the second answer when you are applying the boundary condition 2 in the displacement function. So substitute P is equal to n pi by L in equation 3. Okay, so y of x comma t equal to C2 sin n pi x by L, because P equal to n pi by L into C3 cos n pi at by L plus C4 sin n pi at by L. So this is what the next, can call this as equation 4. So now we have applied our two boundary conditions. What is the next step? Next we are going to apply boundary condition 3. So apply boundary condition 3 in equation 4. So what is our boundary condition 3? Boundary condition 3 is displacement function is 0, that is y of x comma 0 equal to 0. That means we have to put t equal to 0. Okay, so we have to put, that is t equal to 0 in equation 4. So what will happen? The left hand side will become y of x comma 0 equal to, here there is no t, so the first term will become as it is, sin n pi x by L into C3 cos n pi at. So here t equal to 0, cos 0 value 1. So C3 into 1 plus C4 into sin 0. Sin 0 is 0, which is equal to 0. That means we can get C2 sin n pi x by L into C3, which is equal to 0. So two constants are there, that is C2 C3 sin n pi x by L equal to 0. So here already we know that since C2 is not equal to 0 and sin n pi x by L is not equal to 0, so which is the 0? 0 term is C3 equal to 0. So from this we can conclude that C3 equal to 0. So now we are going to substitute C3 equal to 0 in equation 4. So substitute C3 equal to 0 in equation 4. So what will happen? Y of x comma t equal to C2 sin n pi x by L into C3 is 0 plus C4 sin n pi at by L. Okay, so this is what our displacement function. So this can be written as C2 C4 sin n pi x by L into sin n pi at by L. So instead of writing C2 C4, we can take Cn equal to C2 C4. Therefore the displacement function y of x comma t equal to Cn into sin n pi x by L into sin n pi at by L. So after this we have to write the sentences. So by the superposition principle we are going to give the general case, that is the most general solution in the case we are going to give the sigma notation, that is y of x comma t equal to sigma n equal to 1 to infinity Cn sin n pi x by L into sin n pi at by L. We can call this as equation number 5. So up to this the type 2 problems are similar. So only the last condition, that is applying the fourth boundary condition, only differ from every problem under type 2. So now we are going to apply boundary condition 4. What is our boundary condition 4? Boundary condition 4 is dou by dou t of displacement function equal to, it's given in the question. So to apply the boundary condition, before itself we have to differentiate the displacement function partially with respect to t, then only we can apply the boundary condition 4. So after this, differentiate equation 5 partially with respect to t. Okay, because we are going to apply the initial velocity, that is why we are differentiating partially with respect to t, the above equation. So what is our left hand side? Dou by dou t of y of x comma t equal to sigma n equal to 1 to infinity. Here the first term there is no t, so we can write as it is Cn sin n pi x by L into differentiation of sin cos. So cos n pi at by L into what? N pi a divided by L, because derivative with respect to t. We can call this as equation 6. So now we can apply the boundary condition 4 because it is in the form of dou by dou t. So apply boundary condition 4 in equation 6. Okay. So now we can apply the boundary condition 4 in equation 6. So what is our left hand side? Apply boundary condition 4 means what we have to substitute? We have to put t equal to 0. Okay, that is t equal to 0. We have to substitute t equal to 0 because our boundary condition 4, here we have t places 0. So when you are applying boundary condition 4, we have to put t equal to 0. Okay, that is what we are going to apply now. So what will happen? Dou by dou t y of x comma 0, because t equal to 0, equal to sigma n equal to 1 to infinity Cn sin n pi x by L into what? Cos n pi at. So t equal to 0, cos 0 value is 1, into what? Into n by a by L, which is equal to what? Equal to g of x. That is what given in the question, where g of x is equal to what? Where we have taken the g of x as v0 sin cube pi x by L. This function is given in the question itself. So what will happen? Which implies it is equal to sigma n equal to 1 to infinity Cn sin n pi x by L into n by a by L equal to v0 sin cube pi x by L. Okay, so this is what we have arrived after applying the boundary condition 4. So what is our left hand side? Dou by dou t of y of x comma 0. So here we are getting that sigma n equal to 1 to infinity Cn sin n pi x by L into n pi a by L equal to v0 sin cube pi x by L. Already in type 1 also we have seen the question like sin cube pi x. Sin cube pi x, what is the formula? Sin cube x is equal to, this can be written as 3 sin x minus sin 3x by 4. This is the formula for sin cube x. Instead of x, here we are having pi x by L. So this formula only here also we are going to apply. So before apply that, we will write it this sigma n equal to 1 to infinity Cn into n by a by L into sin n pi x by L equal to 3 sin, instead of x we have to write pi x by L minus sin 3 pi x by L whole divided by 4. Okay, instead of this sin cube x we have applied this result. So now look at this, with the left hand side as well as in the right hand side we have the same kind of terms. So in this case we are going to equate the coefficients on both sides. So here we have only two terms, that is sin pi x and sin 3 pi x. So here also we have n terms. So we can give values for n in the left hand side. So when n equal to 1, okay, so we can get C1 n equal to 1. So C1 pi a by L into sin pi x by L plus n equal to 2. So C2 2 pi a, okay, by L into sin 2 pi x by L plus C3 3 pi a by L into sin 3 pi x by L plus etc. equal to what? Equal to, here we have one v0. Okay, so equal to v0 into sin pi x by L minus sin 3 pi x by L whole divided by 4. So now we are going to equate the coefficients on both sides. So C1, the first equating the coefficients on both sides. So what will happen? C1 pi a by L into sin pi x by L. So in this place what we are having, in the right hand side we have 3 v0 by 4. Okay, so which is equal to 3 v0 by 4. Okay, so we need only the value for C1. So which implies C1 equal to, cross multiply this, 3 v0 L divided by 4 pi a. So this is our C1. C2 equal to 0 because there is no sin 2 pi x by L term in the right hand side. Therefore, C2 equal to 0. Now we are going for the next term C3. Here what is in the left hand side? C3 3 pi a by L, okay, into sin 3 pi x by L. So in this place what we are having? Minus sin 3 pi x by L divided by 4. Here we have one V0. So what is this right hand side? Right hand side is minus V0 by 4. We need the value for only C3. We need the value for C3. So C3 equal to minus V0 L, cross multiply this, divided by 3 4s are 12. So 12 pi a. So this is our C3 answer. So now we got the answer for C1 and C3. There is no need to find the C4 or C5 at all because there is a term up to only sin 3 pi x by L. So now substitute the values of C1, C2, C3 in equation 5. We get the required displacement function y of x comma t equal to C1 answer is 3 V0 by L by 4 pi a into n equal to 1 sin pi x by L sin pi a t by L. There is no C2, C2 is 0. So C3 answer is minus V0 by L divided by 12 pi a sin 3 pi x by L into sin 3 pi a t by L. So up to this we have completed the problem. This is the required answer for the given question. Thank you for watching.